Hello, everyone. It's a great pleasure for me to be today with you. I'm also very happy that we have such a cool conference, which is called Quantum Machine Learning. I will not talk today about supervised or unsupervised learning because we were talking about that a lot. So I will not give again a definition, but I'm very thankful to Peter and also to Vedran. To Peter because of this building, which is in Warsaw. I'm from Poland. So probably it could be a headquarter, but actually for Poles, this is not a very nice building because it's related to the communism, so we don't like that too much. But I will relate to your talk and also to Vedran, especially to the subject about these fictitious scenarios that could be taken by an agent. I will talk about the subject of quantum entanglement in time because quantum entanglement is the source for this potential supremacy of quantum computers over classical computers. So when we think about quantum computation, we think mainly about a speed up, which has actually root in quantum entanglement in space. I started to think about quantum entanglement in time many years ago, but it was quite, let's say, awkward idea to try to implement that. But then it seemed that many people in the world started to work also on that. So we started to collaborate. The presentation is a result of discussions and collaboration with people like Jordan Kotler and Frank Wilczek, who are developing the subject of entangled histories, and also people from Bristol, Sandro Popescu and Eliahu Cohen, Yakir Aharonov, who were developing for many years the formalism of multi-state vector formalism. And actually 2 years ago, when I was visiting Google Quantum Artificial Intelligence Lab in Malibu, Masoud mentioned to me that it would be really nice to find some temporal versions of quantum algorithms. And this is why we started to think also about quantum computation in time, and then as a natural relation about some prospects for quantum neural networks and how we can actually steer with the trajectories which are taken by quantum annealing algorithms. It's shifted, but OK. So some quantum fluctuations, as always. So what is the story? What is the story about? The story is actually about consistent histories. These are the roots which I think the father of this thinking about history is Feynman, as you know very well. And it was developed further by Jim Hartle and by Robert Griffiths in their famous, let's say, consistent quantum histories, formalism. But the point is that when you will ask Robert Griffiths, for instance, about consistent histories, the answer is that for Robert Griffiths, there is no such a thing like quantum entanglement as such. This is something very important, that there are still many physicists in the world who don't believe actually in quantum entanglement. Although we in quantum information theory community, we are assuming that this is just given, that this is so natural that we can operate on quantum entanglement as a resource in space. This is I think the most trivial tree which shows a potential evolution of a physical object through different trajectories. And obviously, when you project project evolution at different time steps, you are actually finalizing in a tensor product of projectors, so that there is nothing special in that. So you got actually a consistent history which is separable. And this is why Robert Griffiths, he wrote many papers about consistent histories, proving also that quantum mechanics is local. But then we started to think, I was starting to think actually in parallel to what was done by Jordan Kotler and Frank Wilczek, that probably we could think about modifying a little bit the coherence functionals, which are used for building, let's say, a consistent family of histories in such a way that we could allow for superposition of histories. So actually, when a simple question, what is the root behind quantum entanglement in space? You can generate quantum entanglement in space because you are allowing for superposition of states in space. And we were trying to do the same in case of time. I will let's say, develop that further, allowing for superposition of non-orthogonal histories in time. In this way, actually achieving histories which we are calling as entangled consistent histories. And this formalism has been developing for actually 2 years together with Frank Wilczek and Jordan Kotler. The recent work was about superdensity formalism, which actually brings some tools for manipulation of non-local correlations in time. But in parallel to that, we have another formalism, which is called multi-state vector formalism. I will not go more deeply into that because it would take too much time. But we also are proving that both formalisms can be isomorphic under some conditions. Why this is important that I'm talking about those things? Because people quite often are using let's say in a free way, a subject of quantum entanglement in space, not talking about details. Sometimes it just doesn't make sense to talk about quantum entanglement. Sometimes it makes sense. We started to think that probably quantum entanglement in time could be used also as a resource for quantum computation in the same way as quantum entanglement in space is used for typical quantum computation. And to do that, as a prerequisite, we had to find some appropriate mathematical structures on which we could operate. This is why these discussions about the structure of space, of scalar products, of the coherence functionals are so important. And also, as mentioned by Seth Lloyd, if we are allowing for, let's say, non-orthogonal histories and non-orthogonality in case of the coherence functionals, then we can also talk about quantum entanglement in time, which means that we can actually use this quantum entanglement in time as a resource for quantum operations. This is a very simple scheme for generation of a temporal GHZ state. So this is a temporal version of let's say, spatial GHZ state. And I want to emphasize that the structure is not so simple as it looks like. It's not a mere analogy of spatial structure, because in case of temporal correlations, we always have, which is called in terminology of entangled histories, bridging operators, matching actually different time steps. So we do not have any kind of isomorphism, any plane isomorphism between the extended Hilbert-Spitz spaces in case of such vectors spanned for temporal correlations and spatial correlations. So if we take 4 spins, this is the most simple scenario, we can generate actually quantum entanglement in time, but in such a way that we are just associate with the first spin an ancilla which consists of 3 spins. So why 3 spins? Because these 3 spins will collect some information during each time step about correlations from the past. After projecting at time t3 the ancilla, which is here, to such a state, we can get information about non-local correlations in time for the main system. So this is something which is quite ridiculous, but we showed, and that was also shown by Jordan Kotler and also by Eliyahu Cohen in their formalism, we can generate statistics, quantum statistics, which are not typical for local correlations in space. What is interesting in the whole story is that quantum entanglement in time also is monogamous. So in some sense, we can talk also about monogamy of quantum entanglement in time, which simplifies the whole story. What is also interesting is that we can get analytically Searleson bound for any history with dichotomic observables. So this is what you know from spatial case. But this is not a mere analogy anyway. But I will not go more deeply into the mathematical details. If you are interested, you can just approach me after the talk. If we are talking about quantum entanglement in time as a resource for quantum computation, then obviously the question is, how can we really access this entanglement as a resource? And can we generate, for instance, bound entanglement in time in similarity to what we have in case of spatial entanglement? These are open questions. I don't know the answers behind that. This is the scheme for generation, very easy scheme for generation of statistics, which is non-local in time, where we start with a bipartite system and apply actually some measurements to the main system, which evolves together with the ancillary system. So this is an experimental setup which proves that we can talk about quantum entanglement in time, obviously applying some measures for distribution of probabilities. So this is also a very open field of research for defining actually entanglement measures and protocols for application of quantum entanglement in time and locality in time. And there are many interesting applications related to quantum cryptography in time and also others. And then this is the story about performing quantum operations in time, although this is also very elusive. Quite often people are approaching me saying that there is actually nothing special when you just take a bipartite system which is entangled in space. Then the formalism that we are using is that you have a bipartite system, you are starting with some pure state. Even if this is a mixed state, then you can always purify that. So let's focus on a purified system. And then you are just applying some unitary operation, right? If you have a mixed state, you can always trace out the system, and you can just use some completely positive map. So there is nothing special. And you just start with a bipartite system in space. But we are always forgetting about one fundamental thing, that in physical setup, whenever we are taking two quantum systems which are entangled, the quantum systems are part of the gravitational field, which means that actually the gravitational field also influences the time, which can be related to the subsystems. So whenever we are talking about quantum entanglement in time, then we are talking about quantum entanglement in space-time. And this is why also Seth mentioned about the Wheeler-DeWitt equation, because this is so valid in this case, that we are actually performing computation on a deformed manifold. In the most simple case, we are treating a history branch as a quantum states. So And I want also to say that this paper is under preparation, so this is still under construction. We have actually defined formalism for the gates, but there are some still open questions. The point is that, and this is what I like in this agency discussion about, which was given by Hans, is that we can look at, let's say, a physical object, let's put it like that, in such a way. Obviously, in a physical experimentation, we always state with some preselection. What does it mean that we preselect? Preselection means that a detector, actually, or an observer, correlates with a given history branch of an evolution. So we preselect a system in a given state, and we preselect also an ancilla. So obviously, we can assume that both of them are entangled, are correlated. In a natural way, this is our understanding about quantum trajectories, is that a system, in the same case like an ancilla, they can traverse, obviously, a space-time in infinitely many ways. So we have potential trajectories, which I always like to call these fictitious trajectories, which are not accessible by the external observer. And we have also those which are realized, which are accessed by the external observer. And this is the ancilla, and this is why we are introducing these weak measurements here for steering with the evolution of the system. But what is novel in this approach is that this steering with the evolution should be based on the information which is taken from non-local correlations in time. So not only based on information that we have from the past, but also from the future. But we have to be very careful when we talk about that, obviously, and this is why I put that here. No signaling in space-time and causal relations still hold. And there are always causal relations, because I think you mentioned that might be no causal relations. The causal relations are always kept in the space-time, even if agent assumes that there are no causal relations. So these are the constraints that we are putting on that, right? Which obviously excludes situations that we have in case of special correlations with no signaling, with this bizarre action at distance. Then this is just an example. A trivial synod operation is taken on both branches, so at each time step. But we are defining also some non-trivial synod operations, which take some information from a future state and let's say the present state for the ancilla. And also in this case, I think the funny thing is that people sometimes forget about general relativity theory. That a very simple example is that when you put a clock on your head and on your foot, then the clocks obviously can show different times, right? But this is what is interesting about relativistic information theory, right? That we are always injecting gravitational subject to the whole story, and then the subject is much more complex. This is how the quantum gates can be represented in history representation. This is a very simple case. So in the same case, it would be very interesting to analyze simple models of quantum perceptrons from this perspective, assuming that we have also some locality in time between the output and input, but not in classical sense. So if you are talking about feedbacking, just typical classical feedbacking, then we just have classical correlations. But here we talk about non-local correlations in time. And some questions about correlations with, let's say, quantum neurons. You know very well this, I think, famous picture from the School and Church of Stuart Hameroff about microtubules. But what I like in their discussion is that they are pointing very clearly, that in case of living neurons, we can talk about processing of information at different rates. This is something very, very important. We have processing of information at hertz levels up to terahertz levels. And the processing of information is really very well synchronized. But when we talk with people who are computer scientists or quantum computer scientists, and when we talk about quantum neural networks, we normally think about sequential processing of information, which is actually rooted in our classical thinking. And this is why I think this is also very interesting to try to go beyond the classical paradigm in sequential processing of information. I think the subject is also very interesting from a perspective of, this is the famous, let's say, quantum terminology used by Wojciech Żurek, quantum Darwinism. When we look at these different levels, how the information is processed in quantum, not in quantum, but in living neuron, we can expect that at the most fundamental level, information is processed in quantum regime. But step by step, looking at different, let's say, clock cycles, we have an emerging classicality. Thank you. I think I'm out of time, actually. But this is always an issue, time.
Very close, though. We came in pretty good on when we're only 4 minutes over on the session. That's good.
Yeah.
Any questions? Everybody needs coffee. Me too. Well, actually, I can ask one. Can you go back to the slide about with the very first introduction of the entanglement in time? I think it was
This one?
maybe the one after this one, where you show the experimental setup. Maybe is the one I'm thinking of. Yeah, I'm just curious about the. So how does it? I didn't quite follow this.
So you can because this is a long story about that. I mean,
okay.
about how it's measured. It's measured in, actually, it's divided, let's say, by 3 time slices, like here, and we have a set of detectors, obviously. So what is being measured here? We are measuring here, actually, Jordan and Frank in their Stanford lab. They were measuring, actually counting number of photons. So they defined a measure of entanglement based on number of photons counted. So you can just go, yes, to this, because this is a very long story, so with this measure, yeah.
Okay, let's go get some coffee.
Okay, thank you.
Thanks, everybody.
Thanks.